Activity 96, the electromagnetic spectrum. As it says in the Google presentation, you can listen to this or you can read it on your own, whichever you'd like. It doesn't matter. The one thing that I do want you to do is make sure that you take some notes, make sure that you record the vocabulary, make sure that you're getting main ideas. Stop this or stop your reading and record some notes in your online notebook. I'm going to be looking for them there. So this is a little lengthy. I apologize ahead of time for its length. Here we go. Sunlight is a combination of light waves of various frequencies. Some of the frequencies can be seen and some cannot be seen by the human eye. The reading in this activity explores the nature of these waves, which are electromagnetic. An electromagnetic wave transmits energy that is emitted from vibrating electrical charges such as electrons. The vibrations send energy across distance as moving electrical and magnetic fields, which act as waves. Here is the anticipation guide that I asked you to fill out prior to starting this. Hopefully you have. Here's the procedure. You notice at the end you are asked to fill out the anticipation guide again, but this time the after column. Herschel's famous experiment. In 1800, British astronomer Sir Frederick William Herschel made an important discovery. While observing the sun through colored lenses, he noticed that some colors of the light felt warmer than others. This observation interested him so much that he designed an experiment to try to measure the temperatures of the different colors of light. Interesting. You've already watched that. In this experiment, Herschel used a prism to separate sunlight into the colors of the rainbow. He then placed a thermometer so that it was only struck by one color of light at a time. He discovered that violet light had the lowest temperature as shown in the diagram at the left. Herschel was surprised at this. Oops. Sorry. Hold on. Okay. Here we go. I'm going to try and flip it one back up one more time. Herschel was surprised at this because he knew that violet light was a higher frequency than red light and carried more energy. He then decided to investigate of the unlit area just past the red end of the spectrum. Interesting sentence. He found the temperature on the thermometers rose even higher than it had in the red light. The only explanation for this data that made sense to Herschel was that sunlight must contain invisible calorific rays of low frequency that heat the thermometer. Herschel performed other experiments and found that these waves behaved just like visible light. They were reflected, absorbed, or transmitted. Because these calorific rays have a frequency just below visible red light, later scientists in 1881 established a name for them. And the name was infrared. This name was chosen because the prefix infra means below. Herschel was the first to detect an electromagnetic wave that was not visible to humans. The reason infrared heats things up more than visible light does is related to its frequency. When infrared hits the molecules that make up many substances, it is often just the right frequency to be absorbed by the molecules. This increases the molecule's energy. The increase in energy makes the molecules move faster, which heats up the substance. In a separate process, warm objects also give off infrared radiation as well as other wavelengths of electromagnetic energy. Good time to pause, good time to stop it, and make sure that you have what you need to have. This next section is called ultraviolet energy, and you can see that I have highlighted Wilhelm Ritter. A year after Herschel's experiment, Johann William Ritter in Germany decided to find out if there were waves beyond the violet end of the visible spectrum as well. He conducted an experiment similar to Herschel's, but directed the light onto a chemically coated paper that turned black when exposed to light. He chose this chemical, silver chloride, because it darkened more at the violet end of the spectrum. When he separated the light, the silver chloride was darkest just beyond the visible violet end of the spectrum. He called them chemical rays, which later became known as ultraviolet because ultra means beyond. Ultraviolet waves transmit more energy than infrared and visible light. In fact, ultraviolet has the most energy of all the waves that commonly reach Earth's surface. The energy transmitted to us by ultraviolet waves can be helpful. For example, human bodies transform some of the sun's ultraviolet energy into vitamin D, which is necessary for bone growth. Those people whose diets lack vitamin D and do not have much sun exposure may develop a vitamin deficiency. This results in defective bone growth in children. I'll go slowly this time, hopefully. Not too slowly. Sorry. Oh, come on. Or adults. Lack of sun exposure, including ultraviolet wavelengths, also results in seasonal affective disorder for some individuals who are prone to depression. Scientists have invented machines with which to use ultraviolet light to sterilize equipment because it destroys bacteria, viruses, and molds. At the same time, the high energy of ultraviolet waves poses a danger to people and other living things. They cause damage to living cells, which can result in cancer and cataracts, like those in Tia Anna's eyes. Ultraviolet waves also cause materials such as those used in clothes, furniture, curtains, and car interiors to fade and become brittle. So you can see Ritter's experiment over there on the left with the silver chloride treated papers. Moving on to the next section. It's called Light from the Sun. Try to get it just right, but whether I can or not, we'll see. Herschel's and Ritter's experiments show that there is more energy in sunlight than meets the eye. As shown in the diagram below, most of the energy that reaches the Earth is in the form of infrared, visible, and ultraviolet light waves. The diagram also shows that much of the energy given off by the sun never reaches Earth's surface. This happens because the gases of the Earth's atmosphere reflect and absorb some of the energy. The atmosphere acts as a shield that protects all living things from most of the very dangerous high-frequency, high-energy ultraviolet waves, X-rays, and gamma rays. Although ultraviolet light has less energy than other high-frequency waves like gamma rays and X-rays, it poses more of a hazard to living things because of the large amount of it that the sun emits. If Earth's atmosphere did not have a thick ozone layer, much more electromagnetic energy would reach Earth's surface, causing more harm to living things. So you can see from this graph that here is the blue line, which is measuring or showing you the top of the atmosphere. And you can see this black line is showing you those wavelengths at the surface. So you can see that some of those light waves never get to the Earth's surface. I told you this was lengthy, I know it is. The electromagnetic spectrum. In addition to infrared, visible, and ultraviolet waves, the sun emits a large amount of other kinds of invisible electromagnetic energies. They include radio waves, microwaves, X-rays, and gamma rays. Together, the continuous range of all possible electromagnetic frequency makes up the electromagnetic spectrum shown below. Although portions of the frequencies of the electromagnetic spectrum are given specific names, such as radio, visible, and X-rays, the categories overlap. This is because the wavelength ranges with which scientists classify each type of energy are somewhat arbitrary. It is often hard to distinguish where one group of waves ends and the next one begins. Fundamentally, all electromagnetic energy is of the same nature. For example, all electromagnetic waves can travel through a medium or through a vacuum. They can all be reflected, absorbed, and transmitted through various materials. The degree to which each type will reflect, absorb, or transmit depends on the wavelength of the wave and the surface it hits. Here's the chart that was referred to in the previous paragraph. I'm sure you're looking at it in your book as well. Although electromagnetic waves have common properties, there is an outstanding, it is outstanding, but it's astounding difference in the wavelength from one end of the spectrum to the other. The range of wavelength from gamma rays to typical radio waves is over 1,000 meters. Each range has some unique characteristics. Shorter wavelengths, those from ultraviolet to gamma rays, have the ability to penetrate living cells and damage them. Longer wavelengths of energy, like those in the radio range, can be generated or received by antenna. Our eyes can only detect a very small range of wavelengths from 380 to 620 nanometers. 1 nanometer is 1 billionth of a meter. You can see the things that they're talking about on that chart, and you and your partners are going to talk about that more. You can see the wavelength, how it changed from being relatively long to very small here, from about the size of buildings down to the size of an atomic nuclei. And you can hear the lawnmower in the background. Sorry about that. Trying to flip to the last section. I'm going to have to speak up because the lawnmower is getting louder. Stop it, page. So this last section is extending our senses with electromagnetic energy. There are hundreds of applications of electromagnetic energy. For example, X-rays are used to scan bones and teeth. Remote controls send an infrared signal to a device. Wi-Fi relies on radio or microwaves to send and receive data. Microwave ovens create microwaves to transmit energy to the water and food, thereby heating it up. Some technologies allow us to extend our senses by using electromagnetic waves. One example is infrared imaging in night vision goggles. Night vision technology allows us or lets us see objects by changing the invisible infrared light given off by objects into an image we can see with visible light. Since warm bodies give off infrared energy, a person wearing night vision goggles can scan an area to see people and other warm-blooded animals in the darkness. Additionally, there are detectors that can sense all kinds of electromagnetic energy. For example, astronomers use radio telescopes that detect radio waves by which astronomers see distant objects in the universe. Now that you've finished this, I would like you to go to the anticipation guide and fill out the after column. And once you've done that, I would like you in your group to complete these analysis questions 1 through 5 on page F41. You don't have to do them in an ordinary way, any way that you decide to do that. Include it in your online notebook is fine with me. If you want to videotape yourself and put the video in it, if you want to use Explain Everything on an iPad and put it in your online notebook, that's all great. Whatever way you can show me that you understood the knowledge that you should have garnered from this lesson. So thanks for listening. Have a great rest of the day. Bye.